Good day, everyone. Thank you for joining us for day 2 of the 2-day 12th annual HPC AI Advisory Council Stanford Conference. My name is Brian Sparks. I'm the Director of Worldwide Operations for the Council and be today's moderator. We have a great agenda for the next 4 hours with great topics and speakers, including Control IQ, NASA, University Space Research Association, NVIDIA, and Intersect 360. With that, let's bring back Steve Jones, Director of the Stanford High Performance Computing Center here at Stanford University to help start day 2. Steve, good morning.
Good morning, Brian, and welcome everyone to day 2 of the HPC AI Stanford Conference. So this is our third year now of Zoom. I'm looking forward to next year, of course, Brian, when we're back in person again.
Still working on those dates?
Yeah. So it looks like we're going to be in April timeframe, and potentially a new location on campus with some interesting and new things for people to experience when they come to Stanford in April for our spring conference. So I'd like to take a few minutes here. I think we have a 9:35 start time. Just to mention really quick about some things that I have going with classes, all of these in participation with the Advisory Council. So I have coming up this summer, ME 344 and ME 344S. So one is an Introduction to High Performance Computing. The other is the HPC AI seminar series, which we put on jointly. Both of these are focused on building one focused on building HPC systems. We leverage a lot of the products that come from a company and a person who's going to be presenting here shortly, Greg Kurtzer. So we use some of the Werewolf packages and Rocky Linux and those types of things. So I just want to make sure everybody knows that we have a course focused on that. That one is for matriculated students, but we have a continuing studies course, CS74, Introduction to Building High Performance Computing Systems. That'll be offered in the fall. That one is open to the public at large through the continuing studies program. That's an 8-week course on building systems as well. So we drop a lot into container utilization, those types of things. And we're going to be looking at a lot of the new offerings coming out from Control IQ with that and offering these training sessions. We have a meetup that is monthly where we show how to build your cluster using an automated script. So it takes about 30 minutes to get your system completely up and running with compute nodes and all that. And that's a live session on cluster building. Again, we're looking forward to introducing some of these new things that Greg will be talking about in his talk. So we're at 9:35. I'll take the time here to go and introduce Greg Kurtzer, somebody that I met, I believe about 20 years ago, maybe, could be reaching that amount of time now. I still remember the first time that I met Greg. It was at an advisory council conference. I was working with Gary Jung at that time, and Greg came over and he was with a few other people from LBNL, and they came, and I thought that this was like the power group that came over from Lawrence Berkeley National Laboratory. Like they brought all their top people over and they're sitting there so professional and everything up in the front row. And what I found out later is I think that Greg at that time was like maybe new to Lawrence Berkeley, and they brought them over, and they could have been interns for all I know. But this is when he was starting off his career, at least early in his career. I know that one of the other people that was with him was the equivalent of an intern, and they brought them there to learn something about high performance computing. Not that I was, giving them that advice, but Greg was probably more seasoned at that time. But that was one of the first times that I met. Actually, the first time that I met Greg was through the HPC conference, and this could have been around the time that the advisory council started. So I met him many years ago. We've had a lot of interactions over the years. I have a great deal of respect for everything that Greg has done in this space and for this industry. Most of it's altruistic. His intentions and everything that he does, from CentOS to Werewolf to other types of things that he's worked on. And so I'm proud to have him here today, kicking off this conference, and his new role as the founder, CEO, and founder of Control IQ. I still continue to use a lot of the products that they develop and maintain there and make freely available. And I look forward to his talk today because I haven't heard him speak on a lot of these topics yet. So with that, I'll hand it over to you, Greg.
Wow, thank you. That was a totally cool introduction, and it's a really nice way of saying we've gotten old. Time has gone by, and it has been about 20 years, and I think at some point we were even talking about some of the benefits and pros and cons of Werewolf versus Rocks at that point. It's been fantastic to know you over all this time. And it has definitely been a journey, been a ride. So I'm going to start sharing screen and jump into this. I also appreciate very much you all having me and giving me the opportunity to talk about some of the things that I've been working on with my organization, as well as in the community, and really just being able to share it and share the experiences that I've had. So I'm going to try to fit in as many different topics as I can. So I'm going to go pretty fast, but those of you who know me know I also like to talk. So I'm going to keep watching the time here and make sure that I don't go over. So as we get started, the general idea of this is going to be talking about Rocky, upgrade plans, OS migrations, and whatnot. A little bit about Werewolf in terms of an update, Apptaner, which was previously Singularity, and I'll talk about that a little bit. And then the bigger vision, which we see as what we kind of just call HPC 2.0, this next generation of high performance computing. So to jump right into it, let's start with Rocky Linux. So first off, Rocky Linux came to be because of CentOS, and CentOS was end of life, rather pivoted. It used to be behind Red Hat Enterprise Linux and as the stable, freely available counterpart to Red Hat Enterprise Linux. But it was moved to be in front of Red Hat Enterprise Linux, which means it's a little bit more like a community collaboration point of what is coming down the pipe. Don't necessarily want to call it beta or a rolling release, although it definitely has certain attributes that are very similar to that. But a lot of people, need that stability first and foremost. And that left a gaping hole within the community. To kind of put this into perspective, this is not formal numbers, and I'm quite hoping Addison fixes this afterwards or at some point in the future. But the numbers that I've seen, and just from talking to people anecdotally, it looks like HPC community is about 50 to 75% running or was running CentOS. The rest of the ecosystem is usually about 20 to 25% in my experience in terms of numbers that I've seen. But that is a huge gaping hole to all of a sudden end of life the operating system on. So with the experience that I had from CentOS, early CentOS, starting it up, kind of getting it off the ground and seeing some of the great things that we've done, but also the things that we could have done a little bit better, I was really motivated to try again and to see if we can do this in a way that's going to, again, kind of create that stability within the community and provide a freely available enterprise Linux solution. So we founded Rocky Linux. Now, a couple main pieces: compatible. It is a absolute drop-in replacement for any of the enterprise Linux family of distributions. This includes Red Hat, this includes Alma, this includes Oracle Linux. This did include Amazon Linux, but they've just recently pivoted to Fedora. So that's changed a little bit. But if you're looking for an enterprise Linux solution, Rocky Linux is absolutely a drop-in replacement or a drop-in solution for what you would need there. It is completely open source, community controlled. I am just really amazed at how fast the community came to be. Within 2 months of announcing that the intention to do this, we had about 10,000 people join our Slack. And I think almost all of them messaged me directly and asked how they can help. Having 10,000 people message you is not very helpful, but it would really demonstrated how important this was to so many people within the world and the community. And then the last thing is the confidence. The confidence comes from in open source. And I've said this a bunch of times now. Confidence comes from not having a single company behind an open source project, but to have a lot of companies behind an open source project, a lot of individuals, a lot of organizations. And if they're competing, all the better. So that was one of our primary goals for building up the operating system, is to make sure we are giving that confidence and stability to the open source community. And that was so needed, again, after we just saw CentOS getting pivoted in such a way that was adversely affecting many users within the community. So a couple quick highlights about what we've done within the community and organizations now that have partnered with us and are sponsoring the Rocky Linux or the Rocky Enterprise Linux initiative. Through the Rocky Enterprise Software Foundation, which is the organization behind it. I'm going to just quickly go through this, but I wanted to kind of share what the uptake is like in terms of growth. Last month, when we monitor downloads, we always monitor downloads from the perspective of what we can see visible to us on our tier 0, our primary mirror. And last month we had about 125,000 downloads directly from that tier 0 mirror. In talking and collaborating with other mirrors that we have, and we got about 100 plus other mirrors, tier 1, tier 2 mirrors. We usually guesstimate that it is about double what we see on our main mirror if you include all of the other mirrors as well. So we're looking at about 250,000 downloads last month, and that's been very consistent, about 250,000 downloads per month. And if you consider that every download is pretty much equates to at least one install, hopefully at least one, that's a lot of uptake. It's growing super, super fast. And again, you can kind of see that with the amount of partners that we have listed and sponsors to the project. In terms of future, we have been building a new build system for the operating system. This is going to be released shortly as open source software. It consolidates all of the build steps and pieces necessary to reassemble Enterprise Linux. And again, this goes back into the stability of the community and generating that confidence. Is if anybody can go and retrace our steps and come up with another Enterprise Linux variant, we see that actually as a good thing, because that creates more optionality to people in the community. And that's what people need right now, is that ability to know that, well, they always have choices and they can use whatever they want within that. We have multiple special interest groups that are in progress. A couple noteworthy ones is the Sig Cloud. You can see we've got pretty much all of the major cloud providers, the tier 1 providers that have already joined this. We have the Sig kernel, which is being led by Greg KH. If you don't know who Greg KH is, Linus Torvalds maintains the development Linux kernel. Greg KH maintains the stable Linux kernel upstream. We also have FIPS for any government entities that are out there that are interested in compliance of crypto. Additional documentation, and always more vendor support. In terms of HPC uptake of Rocky Linux, we've seen a massive amount. And this goes all the way back to CentOS. I mean, even Rocky, Rocky Linux's namesake, Rocky McGaw, him, myself, and others even on the CentOS team came out of HPC. So there's always been a big focus from the HPC community driving this resource into the world. And it's exactly the same with Rocky. We have many contingents within the teams that are actually coming from the HPC space. We're also seeing uptake. Not only is my organization really using Rocky Linux as a foundation moving forward in high performance computing, but we also see OpenHPC moving in that direction. Bright Computing has moved in that direction as well, among others. If you're interested in using or upgrading or installing, it's pretty much everything that you'd expect. We've got USB installers. We got a script that you can migrate to it. If you're using config management or provisioning, it all will work as a drop-in replacement. And again, that was one of our primary goals. One thing I just want to touch on real quick, I'm not sure if anyone saw this in the news, but we have recently partnered with Google. Rocky Linux is now being offered in GCP as a tier 1 first-party solution from Google. So you can actually get support directly from Google for Rocky Linux. And we have partnered with them to ensure that they're able to support that community of users. And so I like to call it Go Rocky as Google optimized Rocky, but I'm not sure Google's going to go for that yet. But I keep pushing it. At some point, hopefully it'll just take off. But moving on. Quick update on Werewolf. Werewolf in OpenHPC is at version 3. Version 3 is a number of years old. We're seeing Werewolf, and we've been developing Werewolf 4.0 with some pretty major feature changes, and probably the biggest feature change or two changes. The first one is that Werewolf v4 is now leveraging the container ecosystem for the virtual node file system. This means you can go and build containers and take those containers and use that to provision out to bare metal at a massive scale. That's one major kind of change. The next major change is with something called overlays. You can actually add files, templates, and additional capabilities to each container that are templatized. So you can actually say, for example, that this group of nodes will get this template, this group of nodes will get another template, but all of that is within an overlay that will be provisioned automatically. And it allows you to make changes on top of your operating system, on top of that base container for a group of nodes. Where we're really focusing with Werewolf v4 is on turnkey. We're trying to simplify the deployment of HPC clusters. And one way you can think of this is because it is now integrated with the container ecosystem, it's very easy and possible for people to distribute containers of node images. We've now, as of version 4.3, we have actually put the kernel inside of that container as well. And I know that seems a little weird from a container perspective, but it creates a very nice way for us to include things like GPU drivers, InfiniBand drivers, a Lustre stack, and other things into that container, so we can actually provision out an entire working system from that single container. So a lot of cool features around that. And then we can have different containers for different use cases. We can have IO Lustre kind of OSS containers. We can have OpenHPC containers. We can have containers optimized for GPU, for InfiniBand, and for other things. And each one of those containers can, again, be shared via things like Docker Hub or any OCI registry, and then pull in, and then we can blast that out to any number of nodes. Obviously, Werewolf's open source. It's been open source since 2001, since its inception, and it remains as open source and community led. And then I already talked a little bit about containers. So I'm going to jump into now Apptaner. And again, I'm moving fast here. If you have any questions at the end, please definitely ask. Apptaner is the lineage of Singularity. Singularity at this point has taken off and is fairly well known within the HPC ecosystem. I've given a couple talks at the Stanford conference on Singularity. We have moved Singularity into the Linux Foundation at this point. So the Linux Foundation now is hosting and maintaining the Singularity code base. And there's a couple motivations for it, but one of the big ones was we wanted the ability to cross-pollinate between the different, the ecosystem of enterprise, cloud, and hyperscale that the Linux Foundation, the Cloud Native Computing Foundation, and Open Containers Initiative are all part of. So this gives us the ability to bring that closer to that. And the one request that the Linux Foundation has was, can you please rename the project? We sent out a few notifications and messages to the community asking for name suggestions and whatnot. And then we voted on it, and Apptaner was the choice that it landed on. But I wanted to be very clear, Apptaner is Singularity. just under a new name and now being hosted by the Linux Foundation. So we're very optimistic that this is going to bring really good things, not only to the HPC container ecosystem, but also bringing many of these capabilities into enterprise cloud and hyperscale, and vice versa, bringing the features and capabilities from enterprise cloud and hyperscale back into HPC. And that cross-pollination is really key. So, just a couple things to really just touch on if you're not familiar with Singularity. Singularity is an HPC native container system. And as I've kind of mentioned several times, it is part of the Linux Foundation as an open source project at this point. In terms of future, talked a little bit about bridging the gap. Checkpoint restart is also coming down the pipe. And that's actually a really cool feature, which in Apptaner 1.0 is already available for experimental use. So you can basically, as long as you have DMTCP installed, which is the checkpoint system that we have integrated with, Singularity will leverage that to be able to checkpoint and restore entire containers that are running. And you can even move them from system to system, as you would expect with any container system, any checkpoint restart system. Singularity has the capability to run 100% unprivileged. It can integrate with your PKI, your public key infrastructure, and also can do, in terms of future, and also it could do S3 integration, or will be able to do S3 integration, support for pulling, pushing, and leveraging containers that are up in S3. We've had lots of conversations of integration with Kubernetes. And we're going to be able to do that through something called Fuzzball Substrate. And I'm going to talk about Fuzzball here in just a moment. So I'm going to put that one on hold. But one of the things that I think is really important is how containers have changed how we're looking at HPC across the spectrum. So in HPC, for the last, 28 years, 30 years, we've basically been building the same sort of system. It's been a Beowulf for the most part. We've optimized the Beowulf, and I'll talk about that in a little bit. But for the most part, we've been looking at things the exact same way. Containers were really the first time where we kind of took off our blinders and we looked into the rest of the ecosystem to see what's happening, because there was so much interest and buzz around containers. Singularity was created because the traditional HPC architecture just could not satisfy the alignment of architecture of the container ecosystem outside of HPC. So we had to actually create a container system specifically to match what we need in HPC. Again, that's because they were so distinct and different. But containers are really kind of paving the way. They kind of caused us to look at HPC in a different way. And that continues to grow. So if we start looking at HPC, what is the next generation of HPC? That containers have really kind of started this or sparked this interest. If we start thinking about that, I talk about it as almost like Pandora's box. The container has been that Pandora's box, in a matter of speaking, as it's opened that door to us to start thinking about this differently. We're also seeing HPC use cases getting more complicated. We're seeing job diversity increasing, and we're seeing the types of jobs changing, right? Jupyter Notebooks was just one example of this, but we're seeing this more and more often. And we're starting to see different types of groups become interested in HPC. Originally, it was traditional simulation. But even when I was still at Department of Energy and UC, we started seeing things like really surprising things, like all of a sudden the political science wanted to have accounts on the system. Library science wanted to have accounts on the system. These are organizations that I never considered would be interested in high performance computing, 10 years ago. Now, all of a sudden, they're starting to get more and more interested. So we're seeing the job diversity and the use case diversity really starting to expand considerably. We're seeing interest in different usage models. This is a quote that I get that I've actually gotten by several enterprises who are finding themselves becoming consumers of HPC. And when they basically said, well, we don't know how to do like a system that's designed to do these HPC-like workloads. And I said, well, here's a cluster. Here's how we've been doing it for the last 30 years. It works great. And after I articulate the situation and what this architecture looks like, the response is, well, SSH is for system administrators. And we're even trying to get our system administrators to stop using SSH. Definitely don't want users running SSH and getting access to these systems. So there has to be a better way of looking at how do we get access to these systems in a way that doesn't necessarily require knowledge of Unix command line and shells to be able to do that. Could we actually change that barrier of entry and make that simpler and easier to deal with? For almost since I've been in the industry, well, no, not quite. Maybe about 2005, 2006, every single year management would ask, okay, when are we getting HPC into the cloud? When are we going to move our HPC infrastructure into the cloud? Now, there are some examples of HPC running in the cloud, but it's a very disjoint and not exactly unified system. How do we unify that? How do we pull that together? And how do we make the appropriate decision on what workloads should be running in cloud versus what workloads should be running on-prem? So we have this need, we have this desire we know we should be leveraging cloud, but there hasn't been a really good way of doing that for HPC. So again, this is a major driving force. As you start leaving kind of the traditional simulation HPC space or academic HPC space, go into more enterprise type use cases and commercial use cases, they're thinking a lot about supply chain security. How are they going to gain confidence to make sure that that system is in fact stable and it is trusted and is exactly what they expect it to be running, and that nothing malicious has gotten into there? Democratization, we have to make things easier. We always have to make things easier. And enterprise computing use cases, which I already kind of talked a little bit about. So this brings me into a story. So I was talking to a really big hyperscaler, and they brought me in, and this was about 2.5 years ago. And this big social media hyperscaler, you might be able to guess, said, Greg, we're going to be the biggest HPC system in the world. And that started getting me thinking about what would it be like to build a cloud scale HPC system. Now, in HPC, we've been doing pretty big systems, right? Fugaku, I think, is over 100,000 compute nodes, but those are very kind of optimized, very lightweight compute nodes. But if we were to do this more at a cloud scale, what would that look like, right? We're talking, and typically the way hyperscalers think is they think about building systems in a very different way. So if we start it from how they think about it, which is a rack scale system, they're thinking about it like, let's make it pretty dense. Put 100-ish compute nodes in there. Let's get composable resources, GPUs, disaggregated memory, FPGAs, direct networks, right? So even circumvent the InfiniBand fabric if you can, and just go directly over PCI. Storage, you need a control plane, network switch, and whatnot. But this is a base system. This is one system, right? So if we're going to scale that up like a hyperscaler would, consider this one cluster. So if we have this one cluster and we want to scale up to, let's say, 100,000 nodes, or maybe quite a bit further than that, and these are fully composable and full x86 nodes. These are not thin, lightweight, kind of target-driven nodes, right? These are full standard nodes. It's over 1,000 of those racks. And you now have to start thinking about how are you going to power it? How are you going to cool it? Where's it going to go? And how are you going to distribute this? Because you're not, maybe you could put it in one data center, but it wouldn't be probably the smartest thing to do. And you probably need to think about where's your data as you do this. So how are you going to distribute your data? How is that data sharded? Where is the data? And how do you align jobs going to each one of these separate clusters to where that data exists, right? You have to think about massive number of job sources, or what we call users, right? Very broad job diversity, IAM policies. This whole thing needs to be API controlled, CI/CD integration, and so on and so forth. So even though this got us thinking about this giant scale, and most people don't need a scale of a system of this big, many of these capabilities are what we've been thinking about in terms of a more modern architecture. And we can definitely use this as kind of a pathological use case of how do we build this next level of system, this next HPC 2.0 type system. And there's some additional features and capabilities that we also have to be thinking through. just moving the window out of the way so I can see what time it is so I don't go too far over. Right? We have to be able to support things like traditional HPC, enterprise computing, which we've talked about. Obviously, we're talking about HPC, so performance has to be key and critical. How do we do that also at scale? Data management. How do we make data a first kind of class citizen in terms of scheduling and meta scheduling? Composable workflows, advanced scheduling and orchestration, interface forwarding, cloud integration, just to kind of rush through these. You can see there's a lot of capabilities that we can be thinking about, or we should be thinking about. And, astute engineers can think about how do we layer this on top of our traditional 28-year-old Beowulf model that is flat and monolithic. Could we actually use that as a base? And you might be able to get some of these features on top of that base. You might be able to layer it together, but getting it all in there, it's going to require a lot of shoestring, duct tape, and super glue. And still, I think it would be overly complex. On the same thing on the other side, if you look at enterprise orchestration systems, can they do this? Right? Can Kubernetes do this? Not really. They can't. We've tried that. We've actually already gone down that road. We integrated Kubernetes and Singularity the first time. And what we found is, Kubernetes isn't designed for batch-focused workflows and doing jobs like this. Too much overhead. It's not good at rich policies and whatnot. And honestly, it was just, again, too complicated. So really what we need to do is we need to pick and choose from HPC, from enterprise, cloud, and hyperscale. And we need to pick, what do we want to keep? What do we want to leverage out of these? So we need to cross-pollinate, pull those together, and then innovate, further innovate. And of course, I hope this doesn't come off like a sales pitch, but that's what we've been doing. We were funded, and we started up the company on April Fool's 2 years ago. And April Fool's is just a good way of remembering the date. But we basically were founded to go and create this HPC 2.0 model that was originally inspired by that pathological kind of cloud case that we were talking about. So we have to think about, how do we build this in a cloud hybrid way? We need to be 100% API based, SSH lists, right? We need to be thinking about IAM policies and direct integration with other applications, other interfaces, and so on and so forth. And the whole thing needs to be around the data. We have to follow the data. So I'm going to kind of walk through what we've built. And I usually start it from the user side. So this is a workflow. And it's not, don't get it confused, please, with other workflow languages that exist. This is a little bit different because it's focusing on the ability to do hybrid cloud native computing. And there's other workflows that basically optimize job scheduling and organization of jobs and graphs and whatnot. But this is specific for being able to do hybrid compute. And the batch script just simply did not have enough context for us to be able to leverage it in an appropriate way. So that's why we came up with this format. The format can be easily changed, it could be tweaked, but this is how we approached it, at least for V1. We need to be thinking about three primary aspects about workflows as we're thinking about it from this perspective. The first one is data and volumes. We have to be able to identify all the pieces of data that we need for a workflow. We need to identify and define how do we want to manage and organize that data into volumes. And then we need to be thinking about the compute. The compute isn't just a simple single job. We actually have the ability to have a full acyclic graph in terms of what our jobs look like. How are those jobs going to interact with each other based on everything from interprocess communication to file system access to pipes, right? We have to be thinking about that compute. And then lastly, what are the resources that are needed for this, right? How many CPUs do we need? How many GPUs do we need? Do we need InfiniBand? Do we need what architecture? What microarchitecture? And that's what we've kind of put together into this configuration, right? We've got our volumes. We define a volume here, V1. It's an ephemeral volume, so we'll blow it away at the end of the job. We have some ingress. We have some egress. Ingress happens before the workflow or the jobs start, and egress happens after the jobs are done. The job pipeline in this case is a very simple graph where NCL here requires UFS. UFS requires untar, and untar will run first because it has no requirements. It's using a container. Every job is using basically resides inside of a container, and we can define the environment of that container via everything from environment variables to file system mounts to volumes, what commands are we running inside of each container. And so in this one, we're basically just untarring data. Then we run a UFS model. This UFS model is an MPI job. We're going to run it across 128 nodes. We're going to do the MPI wire up ourselves using OpenMPI. We're pulling the container out of Docker Hub. And we run this job. We're mounting up V1 again within the container. And then when that's done, all 128 processes are done. We're going to then run NCL, which gives us the ability to plot out the results of the data. Now, once this is done, we go back up to the egress and we persist anything we need at the end of the job. So again, it kind of looks like this, right? Input data coming in. We got some container pipelines we're going to run through and output data going out. Now, the organization and in the architecture necessary to run this is obviously not what you'd expect from a traditional HPC system. It's close in some regards, right? We do have a compute cluster, and this compute cluster is kind of similar, I guess, as a traditional HPC system. This isn't a physical layout, so you don't see file systems and whatnot, but there is no home directory storage on this system, but there is a scratch on this system. So however you want to do your scratch is kind of the same as you do right now, but home directory is kind of taken out of the system because we're going to be using some form of an object store or a data lake instead. That can be external to the resource, and we are going to be moving data in and out from that source. So depending on what your network topology looks like, this could be close, this could be far. And we will manage things like where should the job land on which cluster based on the proximity to the data. In this case, we're looking at just one cluster. So we're going to basically pull and push from that data wherever that is. We have, as I talked about, the compute cluster here. We've got a management cluster here. Not to go into a huge amount of depth on this, you'll see there are two pieces of fuzzball. One is substrate, one is orchestrate. Substrate is kind of the foundation. It's a container runtime and VM hypervisor that is API driven and lease based. So you would ask fuzzball substrate, for example, hey, I need 2 GPUs, I need 20 cores, I need this much memory, this type of architecture and whatnot. Can you satisfy those requirements? Substrate will respond with an API that says, or an API response that says, yes, I can, here's your lease ID. And then from that moment on, you have that lease and you can basically schedule things according to that lease ID. Well, when you have hundreds of these systems, if not thousands of these systems, you definitely don't want to be doing that by hand. That's the role of fuzzball orchestrate. Orchestrate is a microservice architecture, so it is going to want to run on top of a microservice platform like Kubernetes. Kubernetes fits this model perfectly because it's very good at that. Kubernetes is not very good at running HPC jobs natively within Kubernetes. Can you do it? Yeah. Can you put a saddle on a cow? Sure. It's probably not the best thing to do, though, if you're looking for performance. So in this particular case, workflow comes in. Orchestrate is going to manage this via a workflow engine. We have a data mover, image service, which is for containers, volume manager, and we have a job scheduler. Inside of this, basically what's going to happen is those leases are going to be obtained on substrate. We're going to ingress the data, create those volumes, run the job pipeline on top of those volumes, and then at the end, egress the data back out. That's a base fuzzball cluster. What is revolutionary about this is the fact that this is just one cluster. The next step is putting maybe one up in AWS or multiple in different availability zones, maybe one in Azure. Maybe you have multiple on-prem systems. Maybe you've got some more up here in other clouds. You can basically run now the third piece of fuzzball, which is called fuzzball federate, which makes key decisions based on where workflows will land based on things like resource availability, cost, and data. And data is interesting because when we think of data, we're thinking about data locality, data mobility, data gravity, and the data security model associated. So again, workflow comes in. We have the same API going into federate as we have going into one of a single cluster. So from a user's perspective, They might be hitting a fuzzball federate cluster, which is many clusters, or they might be hitting a single cluster. Doesn't matter from the API perspective. There's no difference. So user submits a workflow. Fuzzball federate makes the decision on where it should run based on those primary scores. And it will figure out automatically based on the policy that the organization has put in place on the federate side. And it will automatically land it at the right location. Now, excuse me, as I said, Fuzzball is 100% API driven. There's no SSH in order to leverage the system. If you're familiar with Kubernetes, you're probably going to feel right at home with regards to the command line interface. You're going to create contexts, connect to systems. You're going to log into those systems. You're going to run workflows on those systems. You can list the workflows. You can attach to those workflows, so you can actually get an interactive pseudo TTY in one of those to one of those applications. So if it's an interactive application, you can attach to it and get the IO directly from your Fuzzball command line, which again is running on your laptop or on your workstation or somewhere else. You can exec commands and shells inside of these containers. In terms of developing these workflows, we have some graphical tools that we're building, as well as full graphical environments actually as a client to Fuzzball. So you'll actually be able to run Fuzzball not only via the CLI, but via a graphical environment. And workflows are actually very flexible. There's a lot you can do with them. So for example, here's task array, MPIs. And we're talking MPI, we're also talking about specific node resources. Different types of volumes. This is a persistent volume, which is basically when data is already pre-stored and pre-cached associated with a single system. We can ensure that a workflow is going to land on the appropriate system based on that persistent volume. We have a system to maintain secrets within the system. So for example, an organization could have a shared secret for, as an example, the NVIDIA container registry here. And a user can leverage that secret without ever knowing what that secret is. So we actually have a full secret system, which is basically embedded into our IAM policies. This is an example of us basically running the HPL AI benchmark that we tested on a cluster of NVIDIA DGXs. And this actually ran, as you would imagine, exactly as you would expect it to run. But with just this one little script right here, and with Fuzzball installed in that DGX, without anything else, we're now able to leverage that DGX and run any form of a workflow on it. In terms of interacting, again, here's again another example of using secrets to interact with a registry. In this case, we're mining Ethereums. Example of Gromax, Blast, just kind of rushing through these, lamps. You can actually even leverage different GPU and GPU flavors just by changing these two lines. And the last example that I'm going to show you is Jupyter. This is basically the workflow to run a Jupyter notebook. And of course, you can always add all the volumes and resource requirements and everything else that you want to this workflow. But the important two pieces are, what port do we want to run Jupyter Hub on when we run this notebook, and the fact that we're going to catch the network, all network traffic we're going to catch. So when we start this workflow, we look at the last line of when this container runs, and you're going to see it gives you a token, or which is a random token, and it's pointing to localhost. So what we're going to do is we're going to redirect the port from this container, this process running remotely, and we're going to direct it to a local port that Fuzzball is going to basically open up on our behalf. And when we connect to this port, it's going to redirect traffic through the Fuzzball fabric and land it right here on this compute node running somewhere else where we may not even know where it runs. And that means you can just open up a web browser, copy paste this, and it just works. Now, Fuzzball is in early beta right now. We have a number of active POCs going right now. And we would love to know, what are we doing right? What are we doing wrong? What needs work? And how can we basically help? How can we make it better? And so if you are interested in participating and learning more about this, learning more about Werewolf, Rocky, Apptaner, please do reach out to me, give me a call or an email. and I'd be happy to talk with you and even show in more depth exactly what we're doing. So that's all I got. And I'm happy to answer questions if we still have a little bit of time.
Great, Greg. Thank you. We do have a little bit of time. I know Steve has a question or two.
Sure, I'll jump in with a question. So I noticed in the data lake, you had the CI/CD, GitHub, GitLab, Jenkins, et al., Travis inclusion there. So how does that play into it?
Because everything is API going into this system, whether we're talking about Fuzzball Federate or a single cluster, right? Mm-hmm. Because everything is API based and we're using all standard authentication mechanisms as you would find with any other sort of a cloud kind of focused environment, it makes it real easy to integrate with a CI/CD solution. So the CI/CD pipeline itself can actually submit workflows into this system. And we would basically run that, and via webhook, we would basically post a response back to the CI/CD, letting it know it's done and here's the results. So it makes it very, very easy to integrate with pretty much any CI/CD platform that you want to leverage. Okay. And when you're talking about targets, such as local cluster, S3, those types of things, what about any luck with connecting to government systems, sending workflow there? I mean, how is that looking like, a national lab, that type of thing? Is there any work in that space too? Yeah, so we actually have multiple POCs going with Department of Energy national labs. And as you can imagine, I've got a bunch of good contacts at Department of Energy. So we've actually been collaborating quite a bit with several DOE labs. Mm-hmm. And really, just it's funny, just as a quick side. When I first started thinking about this, I thought to myself, there's no way traditional HPC cluster, anybody doing traditional HPC is going to be interested in this. This is an enterprise solution to bring HPC-like capabilities to an enterprise architecture. And that's what I was thinking when I first did this. And then I started running this through colleagues and peers that I know within the industry and said, okay, what do you think of this? What am I missing? Where do I need to be doing better? How am I, what's on and what's off on this? And after going back and forth, the response that I got is we're really, really looking to modernize our infrastructure and be thinking about HPC in a different and more inclusively broad way. This is nailing it. We actually want to leverage this. So I didn't think it would at all go into traditional HPC, but it actually, that's where we're seeing a huge amount of uptake right now, and interest is in traditional HPC, which again is surprising to me. I thought there was so much inertia in traditional HPC that there wouldn't be any interest in this, but apparently that there is. So yes, there are government labs right now interested in it. And I can't say a huge amount on this side, but I can say there's other federal entities that are also very, very interested in this. And one aspect that makes it very interesting is because we are controlling, here, I'll use this slide as an example, because we are controlling this ingress, right? The workflow describes the ingress and where the data is to come from. We control the mechanism of movement of data here, which means that organizations that have very, very strict data privacy and data classification can leverage this to inject their own rule sets and policies as to what users and what applications are allowed to touch a particular piece of data. And so because we control that completely and we have complete records and auditability of that, it actually is a very nice platform for people that are dealing with high security areas.
Okay. All right. So one additional question. So as a service provider, we look at offering things out like Ansys product. And so let's say something like Ansys Discovery, which is Windows-based. And in the traditional Linux environment, we haven't found a way to offer that out. Are you going to have solutions for more Windows-based architectures? Did I miss that as we were going through this, or?
I wouldn't say Windows-based architectures. What I would say is,
or Windows-based apps.
Yeah, see, that's still really hard because we're leveraging containers, and containers are historically running Linux. Right. But what we can do, and what we are doing, is lowering the barrier of entry such that people who are not Unix people can easily run. So you can imagine a situation. We already have a GUI editor that I'm describing here for defining the workflow. We have the ability to define, these workflows, IAM policies, schedule jobs and whatnot that you just don't see in this particular example, but we can do all of that. But there's one other aspect that we can do, which is you might imagine that creating a template out of a workflow is actually a very easy thing to do, right? We can take this and add template macros in terms of inputs, outputs, how many size, how big of a system do we want to run? How many cores, how many MPI, tasks do we want to run? Right. We can put all of that as a template into this file. This file then kind of becomes an application as long as we have a renderer that can properly fill in those templates, those template macros or variables. So imagine another tab on this GUI that basically just says a list of workflow applications. All of, you can have ANSYS in there. You can have, name your application. And then it could be as simple as just a wizard or a form where you basically just put in the right data and hit run. And it
sounds like we could actually take it in a different direction where we use some of their Linux-based apps and then create a nice interface for the user to use it. And then it somewhat models what they're doing with discovery, making it easier to do CFD, that type of thing.
The hardest uptake here is actually containerizing the apps. With many open source scientific apps, it's actually really easy, and most of them have been done and they're sitting up in Docker Hub right now. But many of the commercial ISVs out there have not containerized their apps, and just due to their install process and their licensing, they've made it very difficult to containerize. So we're actually working with several different vendors and actually facilitating that. And we're hoping to actually be able to provide containers with those vendors for people to do this, not only on a traditional HPC system with Apptaner and Singularity and other container systems, but also for things like Fuzzball.
Okay. Those are the questions I have.
Okay. We do have one question coming in. Do you use any native Kubernetes objects to utilize Fuzzball workflows on the public cloud, like underlayer?
Yeah. So great question. So as we look at, I'm going to go back a slide or two. Let me do this slide. Well, first I'll start here. You can build one of these clusters up in the cloud, right? You can build them in multiple availability zones in the clouds and then tie them all together. When we build in the cloud, it's a little bit of a different architecture than what you see here. This is for a static fixed cluster. When we build for the cloud, what we would basically do is provision this Kubernetes layer using whatever tools that they're using for automating a Kubernetes, substrate type, or foundation. And we would just run our microservices on top of that. So we would just basically do a Helm install, run on top of whatever the cloud's providing for Kubernetes. And then that's the only thing you're paying for until you run jobs. And this, by the way, the Kubernetes stack is very inexpensive on clouds. Like they've optimized that considerably at this point. So that's the only cost that you would incur up in the cloud. When workflows come in, we automatically provision the workflows based on configurations that the organization has set. So you can choose what system types, what AMI types, what machine types, what architectures, what GPUs, and you can create a whole class of systems, and we will leverage that map to basically figure out what we need to provision, set up that resource up in the cloud, run this workflow on that, and then the moment it's done, we tear it back down. So the only thing you're paying for is this. What we've found in my experience is cloud does make a lot of sense for HPC, but not as a fixed system, not as a static system, because the cost just is too great. In many cases, it's cheaper just to go and buy it yourself and then just run it on-prem if you're going to run it all the time. But for burst capacity, cloud is almost unbeatable. So if you have bursting where you're going up and you're going giant systems and then shutting it down and bringing it back down, and then you're going again giant and shutting it down, that elasticity is incredibly fundamental to a to a really good cloud experience for researchers and for people. But the way that we currently build HPC systems up in the cloud is not a cloud native solution. This is all completely cloud native. So it does that very effectively and very efficiently. In terms of, there's one other aspect that I think you might be asking about, so I'm just going to proactively touch on it. You might notice this arrow right here going from Fuzzball back into Kubernetes. We can leverage the Kubernetes resources for running services within workflows. So if a particular workflow requires a service, or if you have a workflow that has a persistent service that you want to always have running on the system, or for running for a particular amount of time, we can actually use the Kubernetes resource underneath here for services. We can also use Fuzzball Substrate for services. So this is a decision that would basically happen or be driven by requirements of the workflow and organizational policy. I think I covered both aspects of what you might be asking there. But let me know if I didn't.
Thank you, Greg. Yeah, if any other questions come in, we'll let you know, and hopefully you can answer them as quickly as possible. Really appreciate the keynote, Greg. Thank you so much.
Yep. Thank you, Greg.
Absolutely. Thanks, everybody.